Testing. 1, 2, 3. Okay, I think audio looks good. All right, everybody, welcome back. It is Elijah. Today we are going to be talking about Lecture 12, Chapter 6. And again, sorry for the inconvenience, but as you know, we usually do almost all our lectures in person, but this is kind of one scenario where we had to do it recorded. So I think I made a pretty good lecture for you guys today, and I'm pretty excited because it's a Navier-Stokes equation. And I think out of all lectures, if you were to remember something from this class, this is probably one thing that you should remember. Okay, so let's get into it. And this actually used to be my old, when I used to be a tutor at the QSC, this used to be my old video background. So I don't know if you can see it, but if you know what that is, maybe we can talk about it next time we're in class. Okay, so this is Lecture 12. Chapter 6, Fluid Mechanics. You could win $1 million? What? Why is that? You'll see in a bit why. It's not coming from me, obviously, but you'll see why. Okay, let's get started. So, agenda, our announcements. So, no class next Monday due to holiday rate. So, I believe it's President's Day. It'll be embarrassing if I get the holiday wrong, but it's a holiday on Monday, so do not show up to lecture. I believe it should still be on track, but I will double check things, and if there is a needed recording, I will post it and let you know. If anything, it will just be more of getting the derivations out the way so we can do more examples in person. Okay, for midterms, my goal is to get those graded by Sunday, hopefully. Sorry, it's been a little bit busy, but that is my goal, so you guys can have a better idea what your grades are so far this quarter. Okay, homework 5 quiz is in person next Wednesday, so please be there for that. That's going to be in homework 5, and you should already have been able to do the majority of homework 5 after what we went over on Monday, but this will definitely for sure cover all of the homework 5 concepts. And by February 23rd, you have your project file submission, right? And a few announcements I've made. I need to make an updated file, but right, the 2 equations, one equation has to be from class. It could be anything that we talked about. It can be in this presentation. It could be anything in the textbook as well. That counts. So if you want to look around the textbook, I'm sure you'll find something that applies to your project. And then your second equation could be from a reliable source, or you could do 2 equations from the textbook. And like I said, grades will vary a little bit based on other presentations. And the reason why I'm doing this, I'll talk about it in person too. I've been checking in with groups and talking, I've seen one group might be doing some CFD, some might be doing a Navier-Stokes equation, some are just doing continuity equation, right? Your Q equals AV, which is okay too. But right, if there is one group that's doing all this extra work compared to one that's taking a more straightforward equation, I think the one group that does more work should get a better grade by a little bit, right? But I'm not grading on a curve, right? Because a curve is you have set grades for a set amount of people. So if everyone does something, in the same I guess, difficulty or work they put in. If everyone did like a CFD like another group did, or a pretty complicated equation we learned in class, I mean, everyone can get a really high grade. So I'm not grading you against each other. I'm just saying if one group puts more work in than another group, right, it only makes sense that the group that put in more work should get a better grade. And on top of that, I am considering taking attendance as part of your project grade when we present. To me, I know people don't attend every class, but the majority of you do, so thank you. It doesn't hurt my feelings. I do want everyone to be there, but I don't force you all. But for your peers, though, I think it matters because you are all there to support each other, and you're especially a cohort in your graduating class. So yes, I'm thinking about taking attendance for just the presentation days to encourage you to attend your peers' presentation. Just because I think it's only fair that you're being an audience for each other. If you're an audience for one group and then you present and someone's not there for you, it's kind of just not fair. So I'll think about that more and talk about it more when presentations get closer, but just a heads up, I might be taking attendance for that. Okay, agenda, we're going to finish chapter 6 today. We have the Navier-Stokes equation. I want you to really understand this conceptually, dig it into your brain, because like I said, this and maybe Bernoulli's equation are like probably the top 2 things you should take away from this course. And we're going to look at simple solutions to the Navier-Stokes equation. So that's things that's already been solved for specific cases, and they have a set equation for you to use. And some of those equations will be on your homework. And then we will have a Navier-Stokes equation example, which I already pre-recorded for you. I will post that video, but I will also try to play it in this lecture so you don't have to go back and forward. It's still uploading on my YouTube, so hopefully it's done by the time we get there in this lecture. So, okay, let's get started. And sorry about the looking. I have 3 screens and my camera is over here. So, okay, let's actually get my pointer. Where's my pointer? Okay. Sorry, my voice is a little raspy. It's like 1 a.m. right now. But, we gotta stay on top of things and get you guys going. Okay, so this is we already went over this. This is kind of a derivation of where the Navier-Stokes equation came from, right? So, our goal is to apply a differential analysis to find fluid motion with viscous effects, because we've always assumed in viscid fluids, right? Meaning no viscosity. So these are stress deformation relationships. I went over this last lecture already. So if you missed it, you can look at previous lecture slides or look at the textbook. And here are more stress deformation relationships in polar coordinates. And this essentially is just leading to the derivation, right? Skip this. And like I said, I've been trying to apply your guys' feedback. You want less derivations, more examples. So I put an example for this lecture, hopefully less deriving. The example is pretty long. That's why it's only 1 example for today, almost like half an hour. And you can kind of see why, because these equations are looking kind of big right now. So, okay. So what we end up doing is once we get these equations, and this, keep in mind, I believe this shear stress right here, you will actually be needing for one of your homework problems, this shear stress. So keep those in mind when you're doing homework. So these equations of motions basically came from Newton's second law, which I derived, just F equals ma. And once you get these equations, which I obviously also previously derived, you just plug those into here, and you solve, and you get the Navier-Stokes equation. So I'm not going to go through it because we talked about it in class already, but these are the equations that you need, okay? And like I said, that's kind of where it came from, but you look at this, and what do these terms really mean? And that's kind of what we're going to talk about today, because I want you to understand this conceptually and then do an example problem and understand how to apply this equation. So this is Cartesian coordinates, in the upper right here, you have your x, y, z. Your velocity directions are respective to u, v, w, or we can call this nu. Still going back and forward, but just velocity in the y direction is either v or nu, but this technically looks like a Greek letter nu. Okay, so x direction, these are your equations, y direction, z direction. Thank you, someone pointed out last lecture that there was an error in the textbook that I think it was either this z or this z was not there. So I fixed that. I actually wrote physically in my textbook that this was an error. So maybe we can let the publisher know or something like that. Okay, Navier-Stokes equation in polar coordinates. So if you were to plug in these equations into these equations, you get this polar coordinate equation for Navier-Stokes. Okay, you have your r direction, theta direction, and your z direction, just your traditional polar coordinates. This is already all review because we went over this last lecture. Okay, so this is a little bit new. So this is the condensed Navier-Stokes equation. So if you, like I said, see the memes and if you use Google Navier-Stokes equation, this is probably what you're going to see, right? In reality, this is what it means. But this is just more condensed form, easier to kind of write out. And it just looks a lot nicer, right? So you can see, right, this how these link. So if you just look at the x direction here, density is right here, right? Your partial derivative of velocity with respect to time, right? So that's right here, these terms right there, okay? And then this v dotted with the del operator with another v, these are just your velocity vectors. This is the first velocity vector is these u's, these v's, and these w's to the left of this partial derivative. And then this del operator and this v, right, these are these terms right here. I guess we'll stay in the x direction, these terms right here. Okay, so the left-hand side of the equation is right here. And I'm like, again, I said in the next slides, I'm going to deep dive what these all mean, right? Okay, and here we have on this right side right here, this is our pressure difference, because this is our partial derivative of pressure in the x direction, okay? And we have a negative here, so that's our summation and force, which you'll see in later. But we have x, y, and z direction respectively for the other directions. We have our density and gravity, just so you can see there. And here is our viscosity, mu, which we have learned in, I believe, lecture 1, right? This comes from just a table. And then another del operator, so just partial derivative, taking two derivatives to the respect of your velocity. So a lot kind of happened there. I'm going to deep dive what these mean, but all I'm saying in this slide is, right, these terms are just condensed into this red equation here. Oops. So here is that equation right here. Okay, so this is my favorite slide out of the whole lecture. I think if you were to understand a slide, this would be the one. Okay, and I guess I hope people are watching this lecture. When you have your final, and if I happen to ask a concept question, this slide and what I'm explaining is pretty fair game. And like I said, Navier-Stokes is a very important equation in this class. Okay, so conceptually, right, the Navier-Stokes equation is kind of just two equations that are satisfied, which is a pretty fundamental, like, laws of physics, right? So you have your conservation of mass. In parentheses here, I put continuity equation because the textbook refers to this as continuity. But I do not want you to get confused, right, with your Q equals AV equation, which is in a way also conservation of mass. So this is just your, I forgot this Greek letter, if it's nabda or something, but I just call it the del operator, right? It's just dotted with your velocity vector. So this just means, right, you're taking your derivative with your, with respect to your x, y, and z direction, right? And this is your velocity in the x, y, z direction, and it should equal 0. Okay? So that's conservation of mass. Here is our money equation. This is our Navier-Stokes equation, very important, right? And here I made this myself to hopefully you can understand better exactly what each one of these terms mean, and you can kind of conceptually understand, right? So this row here, right, we all know is just density. And conceptually, this is mass. Why am I mentioning mass? It's because we're going to get to Newton's second law here in a second. But since we consider a specific point in the fluid, we divide by volume, right? And mass divided by volume is just units of density. So that's why we have density here, and that's kind of like our mass. Here we have our acceleration. So we have our velocity vector, a partial derivative with respect to time, right? That's your physics 1 acceleration. This right here is the conservation of mass portion, right? So this will actually be 0 if we assume conservation of mass, which is what we're going to do the majority of the time. right? Because this is 0, this goes to 0, you're just adding 0, so that's gone. Okay? But if conservation of mass is not real, maybe it's like fuel exiting a rocket or something, right? You're going to have to leave this term in there. I don't think we'll be doing stuff for that, but that's why you would have that term here. Okay, and then you have the other side, which is this is your pressure difference, like I suggested, right? It's going to be negative because it's going to be a negative force, which you're going to see in this force summation I'm going to explain in a second. It's just your pressure difference, right? Here you have your gravity force, right? It's just your density times gravity. And here is what's kind of new because we no longer have in viscid fluids, right? These fluids now have viscosity. So this mu is a viscosity constant you can find in your tables, right? This del operator is taking the derivative twice, and v is your velocity vector in the x, y, and z direction. So I kind of repeated what I did last slide, but this is kind of everything laid out for you nicely to understand what the Navier-Stokes equation is. And right, in theory, this is basically just your Newton's second law, right? So like I said, this m is kind of related to your density. This is your acceleration. If conservation of mass is out, right, this is 0. Okay, and then the right-hand side is just your summation of forces, right? So your pressure difference, gravity force, and your friction force. So, right, the big idea here is what if I ask what's Navier-Stokes equation? It's mainly composed of two equations, right? So your conservation of mass and the Navier-Stokes equation, which is essentially your Newton's second law. And that kind of comes up a lot in our class, right? Newton's second law. Okay, I hope that makes this clear, right? And this is huge. You should brag to your friends about this equation, right? And one of my favorite YouTubers, he explains math pretty well, and he writes just on a brown napkin. I think his name is Number File or something. I think he actually has a tattoo of this Navier-Stokes equation, and that's how kind of famous it is. So, okay, let's keep going here. Okay. Oh, here I am just hammering it again. So in short, what is a Navier-Stokes equation? You can essentially model almost any fluid you can think of while using the concepts of conservation of mass right here and the Newton's second law. So that's the whole point of Navier-Stokes equation. Okay, examples of what it's used for, right? It's definitely more than this, but right, it's used to predict weather, right? Depending how the atmosphere moves. Fluid flow for planes, right? For the aerodynamics, getting lift pressures on the wings, fluid flow for rockets, water currents, and aerodynamics for Formula One vehicles, kind of like here. So this equation is very popular, very famous. It's used in many fluid applications for anything in, real world examples or in industry. So very, very important. So here's the interesting thing, and this is why I'm going to get to how you can win $1 million. So application-wise, Navier-Stokes is awesome, right? They probably have computers that can compute things for this already. Or not probably, they do, right? So it's application-wise for engineering, for engineers like us, it's great, but mathematically, we don't understand the Navier-Stokes equation. And it kind of talks about it in the textbook, but this is just kind of me reading about Navier-Stokes, and like I said, it's like one of the more interesting equations in the class. We do not have a mathematical proof or understanding of Navier-Stokes differential equation being a smooth solution. And to remind you from your Calc 1, right, a smooth solution, it just means mathematically the solution is differentiable, right? You can take the derivative. And another way of thinking about this is a small change in the initial conditions or input results into a small change in the output. So the Navier-Stokes in a way can be referred to as chaotic, since a small different input can lead to a very large different solution. And I dug a little bit deeper just so you can understand this more, because it's kind of interesting how this equation is so you know, applicable. We use it to so many things, but there's like a little caveat to it, right? So here, well, we don't understand Navier-Stokes equation mathematically. So smooth solution, right? I already described that. Here is like when you take a derivative, right, of these functions. If you have a corner, a cusp, right, or these kind of examples, these derivatives actually do not exist because you can technically only take a derivative of a smooth function. So that's kind of the idea behind it. And I try to give credit if I take, sources from somewhere. This is from a YouTube channel of like a Calc 1 review. I didn't want to go through my old Calc 1 notes wherever they even exist now, but that's what it means to not be a smooth solution. So, kind of like this example here, a Navier-Stokes flow around a corner, solving the Navier-Stokes equation for the corner of this water flowing through this canal leads to a velocity of infinity at this specific corner. So if you solve Navier-Stokes equation for this model and find the velocity for this corner 90 degrees, you're going to find that the velocity is infinity, which is not right? And mathematically, we don't really know why and the proof behind it. And credits to my YouTuber that I was telling you about that kind of talked about this, and this is his video that I screenshotted. So here, same video I was talking about, I screenshotted this from. There are a few problems called Millennium Problems. I think there's 7 of them. And there is a organization, the CMI, I think it's, when I looked it up, it's some kind of rich business person, that if you were to find a mathematical proof or solution, you would actually get $1 million for this. If you were to solve the Navier-Stokes equation and find proof of why is it that for non-smooth functions, right, we get chaotic solutions. So if you were to solve that, you would actually be rewarded $1 million from the CMI organization. And I remember someone mentioning in class that Captain Anderson was talking about getting our names in textbooks, things like that. But, $1 million sounds pretty good to me as well. So, and if you do not forget your fluids teacher here. Just joking. But yeah, just something to keep in mind. If you're bored, you can try to solve that problem. Okay. And last time I checked too, it has not been solved. I think the closest they had was there's this really smart mathematician. He's on YouTube everywhere, named Terrence Tao or Terry Tao, and I think he made some work about estimating like the Navier-Stokes equation, which gets it. I haven't read it or anything, but I just heard about it, and it's kind of got closer to this problem, but not fully solved. So that is how you can potentially win $1 million. And you can look at the other 7 Millennium Problems to see if you can win $1 million in any different ways, right? Because you are all very smart engineers. All right. So I had this meme, my last lecture, right? Like I said, Navier-Stokes is kind of a long, complex thing that people try to avoid. Here is Bernoulli's that people like more. So after kind of explaining the concept, right, I put my favorite slide in here. So hoping that this complex Navier-Stokes equation has been summarized conceptually for you based off how I explained this. So, right, this is Drake in his hotline bling era. So just a little joke to keep you guys up with. Okay, let's keep going. So simple solutions using Navier-Stokes. So like I said, there has already been solved cases for specific scenarios that we're going to be doing in class, and we have equations for. So there's a principal difficulty for Navier-Stokes, which is a non-linearity arising from acceleration terms, which are these terms, right? I should probably extend this over. So these are nonlinear PDEs, or partial differential equations, which are a bit more difficult to solve, right? Or sometimes kind of get out of hand. So for some cases, the acceleration actually disappears due to the flow geometry, which we will look at some of those cases. So Navier-Stokes works for turbulent and laminar flow, but turbulent velocity vectors could be beyond the scope of this course because it gets a little bit more difficult. So you'll see much of our assumptions are laminar flow. So the following equations are for laminar flow that you're going to be seeing in the next few slides here. Okay, doing okay in time. So here we have a steady laminar flow between a fixed parallel plate. So here, let's go to the figure first, right? So figure A, you see your coordinate system, right? X, Y, Z. You can do your right-hand rule. Here are two parallel plates. I believe these are fixed. And the distance between the halfway part to the one face of the plate where the fluid's touching is h. You have u, your flow of your fluid, and g is your gravity. Sorry, 1 second, my throat's getting dry here. Okay. All right, B is the parabolic velocity distribution of these two fixed parallel plates. So here are some of our assumptions that we have, right? We only have u going in the x direction. We can assume v and w is equal to 0, and we have steady flow, which is kind of similar to laminar flow, right? Or ideal flow. So now we go to our continuity equation, right? Or conservation of mass, we can call, right? It's taking the derivative that is right here. Okay. So in the x direction, that is equal to 0. And we know now that u is a function of y, because we're in the 2D plane. And then here you'll see the Navier-Stokes equation. This kind of fast forwards it, but in the next example, I will actually show you things getting plugged in, because I thought the next example is more important, and I don't want to do too many derivations for you. So in the z direction, right, it's going to equal 0, like I showed here. And then we have the negative pressure with respect to z. Y direction here, we have 0 as well again, because we set over here. And then we have the pressure with respect to y subtracted by the density times gravity. Okay, and then if you move this partial derivative of y right to the other side, if you add this to this side and then do your integral, you get your pressure equation right here with this constant with respect to x. And then for your x equation, you do the same thing here. So you plug these in, you get 0. This is your equations equal to the partial derivative of x. And here is your viscosity, your friction, right? It's applied here because we are going in the x direction. Okay. So now we just do some algebra, some rearranging, right? Move this over here, divide by mu. And then we have this partial derivative with respect to y, taking the derivative twice. And technically you integrate twice, right? Because you want to solve for u here, and this is the u that you're going to get. You have two different constants. Okay, and that's the derivation explained, but we're going to go in depth more in the next equation of how Navier-Stokes is really used for these specific cases. So here, now that you have your constants, right, just kind of like in your differential equation classes, you have your boundary conditions. So u equals 0 at y equals plus or minus h. So, right, that just means at the edge of these layers, right, for the no slip conditions, right, your velocity is 0. That leads to, if you plug that in, you'll get your constant 1 equals to 0. And then your constant 2 is equal to this term right here. You then plug everything back into here, the C2. And then this is now your velocity distribution u. Right, and then going through these variables, right, mu is your viscosity. This is your differential in pressure in the x direction. This is your distance in the y direction. This is h defined in the figure here. And then we can get our volume flow rate Q if we take the integral of u, which is this function here with respect to y, and then our integral boundaries now. This is now a definite integral. It's from h to negative h, right, from here to here. So we take the integral and then we get this, and then this is a new equation, kind of just linking your integral to your final equation. So this is just showing that the pressure difference, right, over the range of L, and L is the point of the distance downstream equation, which represents the pressure drop. So this is equal to this, which is basically your partial derivative with respect to x. So this, use this equation, plug it into there, and then you get this Q, which is your volume flow rate. And then here you also have an equation that is mean velocity, capital V, which is just Q over 2H. And if you plug this in to here, this is your mean velocity or average velocity equation. And right, we know all these variables, right? We have H, right, from this figure here. Delta P, that is your difference in pressure. 3 is just a constant, right? And then mu is your viscosity and L is the length. Okay, and I guess before I move on to this, there is another equation in the textbook called Couette, I believe. I might be mispronouncing that, Couette equation. And it's essentially just another derivation in the equation of this scenario, but the top plate is actually sliding. And I looked through your homework and I didn't see that equation get applied, and so I kind of left that out, but I just wanted to give you a heads up if you wanted to read about it. That is there, and if you wanted to note those equations down. And I guess the reason why I'm bringing these up too is because if anyone's going to take their FE exam, which I also did to get my EIT license, you'll notice in every class, right, just these teachers don't have enough time to cover everything. So you'll see something in the review or in your test for the FE exam that you might have not covered. So when you review, you kind of have to review everything. So I'm kind of just mentioning these equations that I might not go over, but you just might want to keep it in mind, not only for content understanding, but also maybe for your future FE exam. Okay, so now we're gonna go to something pretty important as well in the class. Not as important as Navier-Stokes, but well, I guess this is kind of derived from it, right? So this is a specific case for steady laminar flow in circular tubes. And this guy, Bothell, is mentioned in the textbook. I don't know, I forgot his history, but it's a famous either engineer or mathematician. And you'll see Bothell's law here in a second. But it's essentially an exact solution to Navier-Stokes equation for steady, that should be a Y there, incompressible laminar flow through a straight circular tube of a constant cross-section, which we will see here. So now we will derive a solution for viscous flow in a horizontal circular tube. And here, yep. So here's the derivation. We're going to go through this, and this is going to be more in detail of using the Navier-Stokes equation. And this is kind of like a little mini example of itself of how we apply something to the Navier-Stokes equation. So you can kind of think of it as two examples here. Okay, so here flow is parallel to the wall, and you can look at this figure here. Let's focus on figure A. So here the radius, right, is the radius of the tube. And here little r is the radius to the velocity vector. Theta is the angle. So this looks like we're going to be doing polar coordinates, right? And then we have our z and y direction, and gravity is going down. Okay, so Here, the viscous flow is horizontal in the circular tube, so flow is only going in the horizontal direction. The tube is not up and down. Okay, and then and then B is flow through the differential annular ring. So this is going to be kind of used for later. This is when you have something in the middle of your tube and your flow is kind of just that orange part there. Okay. Sorry, my dog is distracting me a little bit because I think he might need to go out, but I will kind of push through here so we can have a smooth recording. All right, so for this, we are assuming the velocity in the radius and theta direction is equal to 0, right? In the continuity equation, we have Vz with respect to z is equal to 0. And then here, Vz, we are taking it as a function with respect to r. Velocity in the z direction is a function of radius. Sorry, 1 second, guys. Let me do something really quick. Okay, there's random pauses. Please skip through so you can skip through them and keep moving forward here. Okay. So, and again, I guess how we made these assumptions here, since the flow is parallel to the wall, we can assume that the axis is symmetric flow. So that is why you can make these assumptions here. VR and V theta is equal to 0 because the flow is parallel to the wall in the horizontal direction here. So now this is when we actually kind of get into it, right? So VR, V theta is equal to 0. So you can work this through, but anything with VR or V theta is going to be 0. And then anything with respect to Z here is also going to be 0. Right, so this whole term is gone. This whole left side is gone, right? Because these are all V thetas, VRs. Yep, they're VZs. These you can keep, right? The pressure differences. Here there is no gravity in the Z direction, so that's why that is gone. So we keep these here, these gravities here. And then here we have our VRs again right there. We have our V thetas here. So these are all going to cancel out to 0 as well. Okay. So that is why these kind of all cancel out until you get to these portions, which you can still use because this is just partial R, this is partial R, right? So this is only 0. Your VZ is only 0 if it's with respect to partial Z. So these you can keep. So you can plug these assumptions in there, and this is what's going to cross out. You can do that exercise, and you can double check me, but that should be correct. And I guess I kind of want to go into why these are 0, right? Just not listing them right. Axis symmetric flow is with respect to the center axis, the flow is symmetrical all the way around, right? So that means the angle theta is symmetric and the VR is symmetric as well, which is why we can assume that this is 0. Okay. So we continue our derivation for our flow in the circular tube. So in the R direction, right? After all this is crossed out, this is what we get. We have to use this gravity in the radius direction to equal negative g sine theta, and gravity in the theta direction to equal negative g cosine theta. So we plug those into here, okay? And then we have our derivatives for pressure with respect to r and theta, which is right here, right? These 1 over r. So now if you solve for pressure, you can add both of these, right? And then take the integral with respect to either r or theta. And then once you take the integral, you can then get pressure here. And this is what you're going to solve for. And then in the z direction, right, this is what's going to come out here. Same thing, you move this over that way, and then you solve. You start moving more of these constants to the other side, and then you get your you're basically trying to solve for this vz here. So you isolate that, right? You take the integral to both sides. You're going to integrate twice, and then you get your constant 1 and constant 2 for vz there. Okay, so once you get your equation for vz, which is your velocity in the z direction, you then have to apply your boundary conditions. So vz is finite at r equals 0. So that just means in the center of your tube here, right, when r is equal to 0, it's an actual, finite means an actual number for velocity. So your center line, that's what r equals 0 is. And then if you plug that in, right, this vz, and then r is equal to 0, you're going to get this term is equal to 0, and then this c1 here, and then this c2. And then ln of r here is going to be 0. But to be a finite element, a finite velocity, right, you need c1 equal to 0 to get rid of this, right? So once you get rid of this, right, you can plug in ln of 0 in your calculator and see. That is why c1 has to be 0. And once you know c1 is 0, you can plug in that c1, and then you can solve for c2. And then once you plug that in, you solve for c2. C2 is right here. And c2, the vz is equal to 0 at r equals capital R, right? And if we go back to the picture, that just means the edges of the tube here, on the outer tube. Right, so the no slip at the wall condition, velocity is equal to 0 there at the edges of the wall. So if you plug big R for little r, vz is equal to 0 and c1 is equal to 0, solve for c2. This is your c2. And then now you can plug that back in. This is 0. This is now your velocity in the z direction. So here, and this is something that you want to box, right? This is your Bothell equation. Yep. And why can't I finish this? Sorry, my dog keeps wanting to hang out with me. He's sitting behind me now. Okay, so Bothell's law. So this is the important part right here that we're gonna, I believe that you might have a homework problem on this, or you want to write this down. So Q, right, is your volumetric flow. So here you can get this, it's defined in the textbook, but if you have VZ multiplied by circumference of a circle, and then you take that derivative with respect to R, then you integrate, right, both sides to isolate Q. So you have a 2 pi and then integral from 0 to R, VZ, RdR. Right, this is from Cut 4, RdR. But they usually have RdRd data, but it's just RdR. Okay, I'm getting distracted. So once you take the integral from 0 to R, you have Q here, right? And then once you have your Q, you have to use this linking equation that I previously defined, which is essentially your pressure difference along the length of your tube, which is just your partial derivative of the pressure with respect to Z. And then from the integral of Q, what you got, you plug this value back into here, and then now you have your lovely Bothell's equation. And this is, right, your volume flow rate from pi. Capital R is the overall radius of the tube. Delta P is the pressure. H just a number constant there. Mu is your viscosity, and L is the length of the tube. And hopefully I'm not getting too detailed here, but I just like to say the variables so when you're solving these, you know exactly what they are. And I guess also one of the big takeaways, like since we got to this equation, right, this was derived from Navier-Stokes equation. So this is a specific case for the Navier-Stokes equation that we got this answer for. Okay, and here we can also get a relationship with mean velocity, right? This was previously defined. Capital V is equal to the flow rate divided by pi capital R squared. So now you can have this V max, which is this term right here. And then you can, you know, plug in these terms accordingly, and you basically get 2V. And then if you take the ratio of your VZ previously to V max, you get this term here. And then now you kind of get this ratio of your max velocity compared to your VZ here, your velocity in the Z direction. It's equivalent to, right, the 1 minus the small r, which is the radius to the velocity vector, divided by big R, which is the radius from the center line to the edge of the wall, squared. And right, this is just a ratio again from your VZ, right, which is your velocity in the Z direction, compared to your maximum velocity, which is in this figure, since it's parabolic, it's right in the center, right? So the velocity is fastest right in the middle of your tube here, which intuitively, right, is what you would kind of think anyways. Okay, so for steady axial laminar flow for an annulus, so this is also not in your homeworks. I just wanted to share this with you because I think I remember this was in maybe the FE exam I took. It's been a few years back. And I don't know if I remember if this was in my fluids class, but like I said, I just want to make you aware of it, just so if it happens to be on the spot for your FE exam or somewhere, you know, you kind of have an idea where it's coming from. So an annulus is essentially just a tube, but the center is blocked by another solid, right? So it looks kind of like a donut. So here is the side view, and here is the front-facing view. And here is your velocity profiles, right? So now it's kind of similar to the Bothell's law of velocity profile here, but now since we have something in the middle, it kind of applies to the top and bottom here. And here's our axis R and Z. And looking into the tube, right, Ri is your inside radius of the solid that's going through your tube. And R naught is the all the way to the outer edge of the tube here. So then here, I'm not going to derive it, because right in your FE exam, right, you're just going to have the equation on an equation sheet or something, then you got to basically figure out how to use it. And so, but we've been reviewing these terms, but I'm sure you'll figure it out if it's on the spot, right? So this is pressure difference, viscosity, length of tube. I just described this. It says R naught here, Ri in here, and it's just the equation, volumetric flow rate. And then here, I also want to mention that this equation is only valid for laminar flow. So a group asked me that they were going to use Reynolds number, and Reynolds number is also one thing I remember from my fluids class. It's essentially a number that kind of helps you decide if your flow is laminar or turbulent. And I was actually wondering why this hasn't came up in our textbook yet, but I looked it up, I was reading, it's going to come up apparently in chapter 7. So this is just a little sneak peek. Okay, so if you were taking your FE exam, right, your Reynolds number will be saying something like, this is your volumetric flow rate for an annulus. And for this to be correct, you need the Reynolds number to be a certain value. So here is the Reynolds equation for this scenario. Okay, so rho is density. Let's skip d subscript h for now. V is velocity, and mu is the viscosity. So dH is hydraulic diameter. And what is exactly hydraulic diameter? It's 4 times the cross-sectional area divided by the wetted perimeter. What is the wetted perimeter? It's the perimeter, oh, that's a typo, but perimeter that is in contact with the fluid. Let's actually fix that right now. I think I had a steady typo earlier too. Is in contact with the fluid. Okay. So here, right, cross-sectional area, the pi r squared times 4, that's where this is coming from. You subtract the outer minus inner because you only want the cross-sectional area of your donut, the white part here. Circumference is 2 pi r, which is here, and this is your dH. So essentially, probably in your problem, you're gonna, just plug in these values and check what number you get, and then they're gonna give you a number like 2100. And then it's, in this case, for this equation, if your Reynolds number is less than 2100, it's considered laminar flow, right? And that makes sense because, right, if you just look at this, if velocity is lower, you're more likely to get below this 2100 number, and then your flow is more likely to be laminar. Right, and laminar and turbulent, we're going to learn more in chapter 7, but laminar is just more of your steady flow that's just easy, ideal flow, right, incompressible, what we've been making those assumptions. Turbulent is when your flow is kind of going more crazy, is more unpredictable. You're going to need different equations and assumptions for that. So this is just a sneak peek to Reynolds number. And like I said, we're going to talk about this more in chapter 7. But for people working ahead, you could use this for your project if you need to. And I guess I'm also sharing these equations because these might be applicable to your projects that you might want to use, even though these are not in homework or anything. Okay, so now I picked an example for the Navier-Stokes equation. And right, this whole lecture is about the Navier-Stokes equation. And we talked about where it came from, the derivation. We talked about conceptually what each term means and what increasing something does and the whole concept behind it. And now this is actually solving for quantities within the equation, so an actual application. So hopefully the Navier-Stokes equation is really coming together in your head now, in your brain. So here, I made a YouTube video for this, and it's about 30 minutes long. I posted the solution right here. You can see maybe why it takes 30 minutes long. It takes a lot more time to write it too. So feel free to go back and forward when you do this. So I explained the problem and everything in the video, so I'll probably just link that in Canvas. But if it works out, I'm gonna kind of read this problem and talk about it, then play the video. That way so that's why everything's in one video. So the Navier-Stokes equation example, right? So the velocity of a fluid particle is moving along a horizontal streamline that coincides with the x-axis in a plane. Its two-dimensional, incompressible flow field was experimentally found to be described by the equation u equals x squared. So this u, right, as we've been seeing, is your velocity in the x direction with the function x squared. Along this streamline, determine the expression for A, the rate of change of the new component, which is your y component of your velocity, with respect to y. Part B, the acceleration of the particle. And then part C, the pressure gradient in the x direction. And you can assume that the fluid is Newtonian, right? And from the, I think, first two lectures, we explained that Newtonian is a linear relationship from your how your viscosity behaves with your shear stresses, right? It's linear. So here I worked ahead, and this problem in the textbook, there's no figure, but I think it's okay to work ahead, right? I'm giving you the answer anyways, so you can conceptually understand kind of what's going on. So u here is your velocity in the x direction with the function x squared. You'll see your velocity in the y direction is going to come out to negative 2xy. You'll see once I work that solution. But once you plot your vector field, right, you have your velocity in the x direction and in the y direction. And if you pick points along your, your four quadrants of your graph, this is what your velocity flow will look like as a vector field. So here you can see along the x-axis, it is just only has a u component or an x direction, right? So there's no y component there. So that's something to keep in mind when you're solving this problem and you're listening to my example here. And I made these two notes. You'll see I rewatched my video and I kind of talk about it, but I think I could have explained it a little bit better. You'll see once you get to this part, you can play the video now if you have it linked in Canvas. But just explaining this, once you solve for nu here, you have your f of x constant. And this just goes to 0. And I kind of wanted to explain further why that goes to 0. So, right, y is equal to f of x, because if you have a function with respect to x, your output's going to be y, right? Just your Calc 1 input output stuff, or even your pre-calc, right, class. And the nu, which we solved for, was negative 2xy. And we know that nu is equal to 0 along the x-axis, right? Because this x here, it says it coincides with the x-axis in a plane, which is right here. There is no y component here, right, which we can see. So nu here is equal to 0. So that's along the x-axis. So if this is equal to 0, this means that this y has to be equal to 0 to make this nu equal 0. Meaning, if y is equal to 0, f of x is equal to 0. So hopefully that made more sense. You can kind of read this backwards in the end, right? This f of x is equal to y because it's a function of x. And this needs to be equal 0 because nu is equal to 0, and nu is this. Okay, and then also I think I kind of glossed over this term here. Partial derivative u with respect to t and partial derivative nu with respect to t. And this technically just goes to 0 because it's respect to t, right? And we don't have any t variables. So, right, taking a derivative with respect to a variable that's not there is essentially a constant. Derivative of a constant is 0. So this term is still part of your acceleration. It's just equaling to 0 there. So, all right. These are the two slides you need for the example problem. I just re-put them in there so you can easily follow, and it'll be also in the video. And we finished chapter 6 basically, so thanks for hanging in there with me. We went through the Navier-Stokes equation, we understood it conceptually. We went through simple solutions that's already been figured out for us for the Navier-Stokes equation. And then we have an example that I have a video for you. I will link that and I will see if I can play it in here, but I don't know if the audio will be good. Yeah, announcements we already talked about. So Yeah, and after everything we talked about, you should be able to now fully do your homework 5. I think you should have been able to do the majority of it already. Oh, and I guess another announcement, right? Your quiz for online is due end of day 216. I've been posting some announcements about that. If you have been keeping up. Okay. Okay, so what I'm going to do now, let's see if my YouTube video is done. It does look done. Okay. Let's make this public. And like I said, if there's any questions, feel free to email or ask me. Sorry, I got distracted a little bit sometimes because my dog made it to my bed and he wanted to sleep there. I usually try not to let him, but he got on there today because we were lecturing. So, okay. I have the video. I'm going to publish this now and then see if I can play it through this screen recording. Okay. 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 So let me check the audio. Okay. I'm not sure how this audio is going to play out. I will leave my mic here and play this video. Worst case, like I said, I talked through the example already in this video, so you'll be able to see it worked out. Worst case, I'll just link it. So, all right, so let's make this a big screen. And I really tried my best to make this kind of look nice, but I'm part-time faculty, right? And I mean, I don't even know if they get the nice fancy iPads, but I don't have a fancy iPad basically. So I wanted to do like an interactive example, so I'm not just reading through off a screen for you, like what I did the whole lecture. So here I just got my little action camera that I use for snowboarding. I showed the problem and I put out my chest mount, and then I did the problem on pencil and paper. So, all right, I'm gonna play it now, and let's get to a good spot. I'll just play the whole video. But if this is just repeating me going over the problem, you can skip over this if you'd like. Just fast forward the video. All right, I'm gonna leave my mic here and play the video, and that will be the end of the lecture. About 1 hour and a half, which is sounds about right because your quiz should take 30 minutes. So it's pretty much if we had lecture on Wednesday. Okay, let's play the video, and thanks for watching, everybody.
I'm gonna fast forward this so you don't fall asleep. This is the Y direction.
checking my work there. So, and like I suggested, that derivative with respect to t goes to 0. That's why when you see me write it here, it's not going to be there. I'm just noticing now that this quality is not that good. I don't know if it's my camera, so it's probably helpful. I already probably would have posted the fully written out solution for this, so that might be helpful to just have that on the side so you can view that more easily.
I did that so I didn't have to keep writing it over and over. But you'll, like I said before, right? The term that has the derivative with respect to t, that goes to 0. Alrighty. So quality was not as good as I expected. So I will post the solutions. Sometimes it was good. I think when I zoomed in, the quality went a little bit down. So I'll post that. If you want to work through it, I would have those side by side. And that example, I think, is pretty important. I think if I were to have like a final, that might be something similar I could do. Just because you pick different parts of the Navier-Stokes equation, and then you solve for certain parts of it, right? Just in variable form. So, okay, that is it. We're coming up exactly at about 1.5 hours. So, thanks for bearing with me and doing this online lecture. Like the video said, email me with any questions. No class Monday. We'll have a quiz on next Wednesday. You have your online quiz due Monday night. And happy Valentine's Day in advance. I have a date with your midterms to grade, so I will be grading those. Okay. All right. Have a good weekend, everybody, and I'll be here if you need anything, and talk to you soon. All right. See ya. Bye.